Okay, so the plan for today is to finish Newton's method. We'll briefly kind of talk about basins of attraction, just because it's kind of a cool little topic related to Newton's method, and work on 4.9 antiderivatives and start into chapter 5. So that is the goal for today. Two quotes of the day for today related to chess, but I think also relate a bit to life more generally. One is by previous world champion Emmanuel Lasker. When you see a good move, look for a better one. And another one by current GM Maurice Ashley. There are three types of trades: forced, fantastic, and foolish. If it's not forced or fantastic, it's foolish. So trades, trading one piece, one of your pieces for one of your opponent's pieces, or essentially choosing a move that would likely cause your opponent to accept that trade. Um, well, that kind of fundamentally changes the nature of the game from that point forward. So, you don't have to make a trade on every move. You can just move your pieces, but a lot of times people like to make trades, and this is kind of his point: is if it's not forced, or if it's not fantastic for you, if you're not giving up, like, giving up your bishop for your opponent's queen or something, then it's foolish. And Lasker, when you see a good move, look for a better one. So, more generally, maybe when you're making a big life decision, or the potential impact of a decision on your life, then maybe the more thought, or uh, the more conservative you might want to act in those situations. So, how much effort should you put into a homework set? Not a hugely consequential decision. How much effort should you put into studying for the final exam? Maybe of a little bit more consequence. If you have a couple of different job offers, maybe one requires you to move out of state, but maybe it pays a little more. Another one, you can stay local, but pays a little less, right? That might be an option where you might want to um, give at the very least a little more thought to something like that, or maybe act a little bit more conservatively, rather than taking the big risk. Uh, but some people, have the mentality that they like to take the risk, and you know, if you're if you're young and you can absorb that risk, right? Like if you don't have a family to support, and if things go wrong with the out of state job, you can always move back and make things work out. You know, when you're young is the time to take such risks if that's your preference. Okay, so on to Newton's method. I mentioned last time that one of the downsides of Newton's method is that uh, if a problem f of x equals 0 has multiple solutions, it can actually be really hard to tell which solution you're going to converge to for an initial guess. It's not necessarily true that if your initial guess is kind of close to a certain solution and kind of far away from other solutions, it's not necessarily a given that Newton's method will converge to the closer solution. It's always true that if you're close enough to a given solution, Newton will converge to that solution. But close enough could be extremely close. It could be 10 to the minus 15 away. So, that's more of a kind of a mathematical theorem type statement than necessarily a practical statement. And, on the real line, if you just went and say uh, if you colored the intervals of the real line that say converge to solution one, green, and solution two, blue, and solution three, red, for a single variable problem or for a real valued problem, you'd have like a line that has some, different color intervals. It doesn't look too cool. But if you look in the complex plane, we can apply Newton's method to the complex plane. So we're looking for solutions of z cubed minus 1 equals 0. Um, or is this, I guess this would be z cubed. Yeah, z cubed minus 1 equals 0, and these solutions should be positives. That should be positive, that should be negative. I had just a sign wrong on this one. Yeah, that should be positive 1. And then I think these should be negative. I might have some signs wrong here, but I think this is right now. I just had a typo on the sign for this one. But this is just pulled off of the Wikipedia page for Newton fractals. You can look at that page. It's an interesting page. It has a lot of different fractals. Um, but this has solution z equals 1. So that's kind of, say roughly over here. This is the real axis and the imaginary axis. So z equals 1 is somewhere over here. And you can see that solutions that are close to, or initial guesses that are close to z equals 1, say like here or here or here, they converge nicely to z equals 1. The same with solutions that are in the negative real side and positive complex side. So maybe there's a solution up here, and initial guesses that are pretty close to it converge to that. Those are the green points. And then a third one down here, and again, solutions or initial guesses that are close to that solution converge to it as well. Those are the blue points. But we also see that, there are some solutions up here, say, that are blue because the points in that little almost like diamond shaped region end up converging to the bottom left solution. Or there are some points, over here in this little red tiny region, they converge all the way over to the way off to the right to that z equals positive 1 solution. So it actually makes these really cool pictures, these fractal types of pictures. So a lot of interesting math behind this and what these fractals are, how they work, and everything. But anyway, these basins of attraction, I figured I have to at least mention them because it's just kind of a cool application. So I think this has a relation to the Julia set. That's kind of a famous fractal. So anyway, you can read up more about it on the Newton fractal page on Wikipedia if you're interested, but that's just kind of a side note. But this just illustrates, you can see how colorful this picture is. It's not just 3 regions like this, that are green, blue, and red in each region. It's not just like we converge to the root that's closest to us or something like that. Kind of another side note of a little bit of interesting math. This is really tangential, but if you take, say, a certain plane and you have a couple of points of interest and you want to separate out this plane into, say, 3 different regions, where for any point that's, say, closer to this point than either of the other 2, it'll be in this point's region, and same for the other 2. So you want a picture that looks something like this, and then something like that, so that all of the points in this top left region are closer to the top left like index point than either of the other 2 points, and the same thing for the other 2 regions. These are called Voronoi cells. I think it's Voronoi. It's something like that. I might have the spelling a little bit off there. But that's actually some kind of interesting math and interesting, computer science and programming and so on, interesting applications there as well. That just made me think of if Newton worked the way that we might, naively expect it to work, I think that would be a good guess that it should work that way, that, whatever your initial guess is closest to is what it converges to. That would be like a Voronoi cell type of map or type of problem, but that's not what actually happens. Okay. So little aside, little tangent for Newton's method. A little bit of fun math, I suppose. When I was in college, I subscribed to this peer-reviewed journal for a couple of years. It was called the Journal of Recreational Mathematics, and it was kind of cool actually. Like, there are people who do serious research in recreational mathematics and math that doesn't necessarily have like an obvious immediate application and doesn't really seem to like fit in with theoretical math or mathematics or pure math or something like that. It's things like analyzing games and things like that, and kind of a cool topic. All right, so end of digression. Back to regular scheduled programming. We're going to do 2 more problems in Newton's method. Recall the Newton's method algorithm. We start with an initial guess we call x naught, and we suppose that it's near x star for whatever that means. We'll then iteratively compute the next guess, an updated guess that's hopefully better than the previous guess. And remember, we compute this by basically replacing the function f of x equals 0 with its linear approximation L of x equals 0, solving the linear approximation instead of the function. And that's what gives us our next guess. So then we get the next guess by taking the previous, or I guess the next one by taking the current minus this update, f of xn over f prime of xn. And then we stop when either we have a small output and a small update, or we saw that Newton can kind of fail to converge. So we want to have if we're programming this in a computer, we want to have like a safety upper limit. We might set n max to be 10 or 20, and if we've done 10 or 20 Newton steps and it hasn't converged, it's probably not going to converge. We would end the program and kick out an error message that says, hey, it didn't converge. Otherwise, we would terminate the program successfully and say it converged. This is my best guess for what x star is, and this is the update and this is the error at that point. So let's look at this next example. Let's find the Newton update for solving 1 over x minus a equals 0, which obviously has solution x star equals 1 over a. Okay, so we're looking at f of x equals 0, where f of x equals 1 over x minus a. That's not 1 over x minus a, but 1 over x minus a, like that. We know then that f prime of x is negative 1 over x squared. And our update, xn plus 1, is xn minus f over f prime. Like that. Or that's xn minus, well, my negative 1 over xn squared makes that a plus. And then my xn squared flips up top as an xn squared over xn, that's xn. And then minus, that minus still sticks around. A times xn squared. Or I can make this a little simpler. I see I have 2xn minus axn squared, or that's xn times 2 minus xn. So my Newton update has one multiplication between a and xn, and another multiplication between xn and the parentheses. A lot of times when we're evaluating how costly a program is to run, if we have a function that needs evaluated, like a nonlinear function, that kind of takes precedence over anything else. So we'd count number of function evaluations. The kind of next most costly thing, kind of roughly speaking, is multiplications. So if we don't have any function evaluations to do, we count multiplications, and multiplications usually cost quite a bit more than addition or subtraction in terms of processor time and CPU cycles and things. So we have 2 multiplications per step. So that's actually pretty cheap, right? We don't have to do any function evaluations because we did the simplification ourselves to get this down to just doing multiplications. And what's the benefit of this? Well, computers are actually, I mean, some of this has changed, over the course of time as processor design has gotten better and better, but computers are actually a lot worse at doing division than multiplication. So it could be optimal for some processor architectures or some assembly languages to actually run a few iterations of Newton's method where we have to do a couple multiplications each step instead of directly trying to do a division. So in other words, if I want to know what 1/7 is equal to, well, I could tell the processor to do 1 divided by 7, and it could try to do that. Or I could start with maybe 1/8. Well, that's a binary number. That's actually really easy for the processor to do. Um, well, not it's a binary number, but it's a number that's works very nicely with binary. Um, so it's 1/2 cubed. So we can start with x naught equals 1/8 and then do a couple of Newton steps. So x naught equals 1/8. Then x1 is going to be, well, we take this update with a equals 7. It's going to be 1/8 times 2 minus 7 times 1/8. Or that's going to be 1/8 times 2 minus 7/8, or that is 9/8. That's 9/64. And we could apply this a couple more times. Let me switch up my share here. There we go. So if we start with, let me clear this out. We start with 1/8. And then my next is going to be my previous answer times 2 minus a is 7 in this case, times my previous answer. So I'm down to 0.140, or 0.141. 1/7 is 142857 repeating. So we see we have, and 1/8 is 0.125. So in 1/8 we have 1 decimal place of accuracy. And x1, 9/64, we have 2 decimal places of accuracy. Coming back over to the calculator, we can just hit the enter button again, and it'll perform the previous calculation again, which will now refer to the 0.140625 answer as the previous answer. So 0.142822. So we went from 1 digit of accuracy, 1 decimal place of accuracy, to 2 to 4. This is what we expect with this quadratic convergence. X3 would then be 0.14285713. So we got the whole 1428571, and then that 3 should be a 4. So we're up to 7 decimal places of accuracy, almost doubled from 4. And I think if we do it one more time, yeah, we see 142857, 142, and then 85 would round up to 9. So at this point, we're accurate to as many decimal places as show on the screen of the calculator. So that's what, 10 decimal places? So if we can kind of get 1 decimal place to start with, and if we need, let's say, 15 decimal places of accuracy, so 1 to 2 to 4, 8, 16, that would be uh, 5 Newton guesses, or 4 yeah, x5. So we have what? We have 7 decimal places of accuracy in x3. X4 would be 15 decimal places of accuracy. And x5, we probably wouldn't improve the accuracy at all, because at that point we're down to the accuracy that the processor or the computer or the architecture or whatever is able to handle. So most likely, again, there's all kinds of nuances and exceptions and so on. And computer science folks are very smart and they found ways to get more accuracy, but that requires some programming tricks and so on. So we can do, what do we do? 2, 4, 6, 8. We did 8 multiplications. Is that better than doing 1 division to get 15 decimal places of accuracy? It very well may be for some architectures. Okay. And as an aside, the multiplications all had to do with powers of 2. That was another, really important component of this. Except for this 7 here, everything else is just powers of 2, which is just shifting bits back and forth. All right, now let's take a slightly different approach. We're going to use Microsoft Excel for this to keep things a little more organized. We're going to estimate pi using Newton's method. We want to find a root of f of x equals cos of x over 2, where x naught equals 3. So I'm going to make myself an index column and an x sub I column. So this is like index 0 and x0, x sub 0 equals 3. I'll have an update column. And maybe I'll actually do it this way. I'll have f of xi, f prime of xi, and update, and then x sub I plus 1, my next guess. So I see that f of xi is going to be just cosine of xi over 2. When I enter a formula into Excel, if you don't have experience with Excel, that's not a problem. It's not required for this course. I'm just showing how you could use a different technology. You can certainly use your calculator to do this, but it just is a little more tedious. So f of xi, I want to do equals. So if I just do a number like, or a problem like 5 plus 7, I type that in. Excel just looks at that as characters. It just says display these pixels in these places, and that's all. If I append an equals to the beginning, equals 5 plus 7, that tells Excel, hey, what comes after the equal sign, I want you to actually interpret as some kind of expression that I want you to do something with. So 5 plus 7, a mathematical expression, gives me 12. So here I want to do equals because I wanted to compute a cosine. I'll just do cos of, and then what number, I want to take this number. So I just click on that cell. So it's going to reference cell B4 divided by 2. So there's f of xi. This is the output that I'm looking for it to get small in magnitude, get close to 0. What's f prime of xi? Well, I need to compute that. F prime of x is going to be negative sine of x over 2. Cosine differentiates to negative sine, and then I get a factor of 1/2 that comes out. So f prime of xi is going to be equals negative sine of xi over 2, end parentheses, and then again an over 2. So the input into the sign is an over 2, and then end the parentheses, and the output of the sign also gets divided by 2. So that gives me this. My update is going to be this whole bit here. I'll leave the negative on it. It's going to be equals negative f at xi over f prime at xi. And then xi plus 1 is going to be equals my current guess plus my update. I wrap the negative sign in with the update, so I will add these now. And then maybe just because we obviously know what the solution is, we can look at the error, and that's going to be equals absolute value of this guess minus pi. Oh, got lazy with my parentheses there. I need pi with parentheses to put in the number pi, and then another parentheses. Okay. So we see we're already at 3 decimal places of accuracy, pi being 3.14159 or so. And now the really nice thing I can do is this index column doesn't actually do anything, just keeps us kind of sorted out. I can say that my next xi, x1, is just equal to this number over here. So this xi plus 1 on the I equals 0 row corresponds to xi on the I equals 1 row. So this cell, if I put it in bold, shows up a little better, wraps around and comes back over here, and we start the process again. I can click and drag each of my cells. Just clicking on this bottom right-hand corner and dragging down. We see we're already at 3.14159. And we see we're already actually at 12 decimal places of accuracy, just with one iteration. Or I suppose 2 iterations, because this is actually x sub 2. And we even see that once we get down to x sub 3, Excel is actually calling the error 0. Of course, it's not exactly pi that we've reached. It's just that it's beyond the tolerances of Excel. Something like a smaller error than 10 to the minus 15 or so, and Excel just calls that 0. Okay. I also notice that I have so normally I wouldn't know what my error was, right? If I knew what my error was, I would just add it to my estimate and get my exact value. So this is kind of like information I usually wouldn't have. I just happen to know pi to a lot of decimal places of accuracy, or at least Excel does anyway. But what I would normally be looking at is, see, can I fill these in? Yeah. I'd normally be looking at these two columns. I'd be looking for a small output and a small update, right? For x1, I mean, 10 to the minus 4 is a pretty small output and small update, but with even one more iteration going to x2, we're down to almost the limits of what the computer can handle. 10 to the minus 13 and 10 to the minus 12. So this is an example, another example where Newton converges very quickly. Any questions so far? All right, let me switch my share back to OneNote so it shows up a little bigger on your screen. I think I can confidently get rid of Excel now. Okay. All right. Any questions on Newton's method before we move on? Okay, so moving on then to 4.9 antiderivatives. So 4.9 antiderivatives, as kind of the name suggests, they're kind of the opposite in some loose sense of doing a derivative. It's the inverse operation of differentiation. So we say that big F of x is an antiderivative of little f of x on an interval I, if it's true that big F prime of x equals little f of x on I. We have a theorem related to antiderivatives, and that is that if big F is an antiderivative of little f, then the most general antiderivative of little f is big F plus c. So if I take little f and find an antiderivative of it, all other antiderivatives will be off only by a constant added on. We actually did this proof back in section 4.2 for the mean value theorem, where we argue that if two functions had the same derivative, then those functions could at most be off by a constant term added on. So you might say, okay, how do I compute an antiderivative of f? Is there like a limit formula or something like that? And the answer is, well, in practice, anti-differentiation basically amounts to a table lookup. Through chapters 3 and 4, we have encountered lots of functions and computed their derivatives. So for instance, I know that the derivative of e to the x is e to the x, the derivative of log x is 1 over x, derivative of sine x is cos x, derivative of sinh x is cos x, derivative of x is 1, derivative of x squared is 2x, and lots more. So we have the understanding of lots of specific functions and their derivatives. And then, of course, we can branch out and we can say, well, we also know derivative properties, that the derivative of the sum of two formulas is the sum of the derivatives, that we have something like the chain rule. So the derivative of like, sine of 2x is probably going to look kind of like cosine of 2x, right? Or the derivative of e to the 2x is probably going to look a bit like e to the 2x. We don't want to take that too far. The derivative of e to the x squared isn't going to quite look like e to the x squared. That's taking a little too far. But quite often we can make an educated guess, if not get the answer immediately from something like a table lookup. So let's go ahead and just do some examples. I think that's the best way to illustrate this point. So I'm looking for the most general antiderivative for each function. I'm looking for big F, the antiderivative of little f, where big F prime equals little f. So if I have a little f, f of x equals 2x, and I want its antiderivative, I'm asking 2x is the derivative of what function? Well, I see in this line, 2x is the derivative of x squared. This would say that f prime of x equals 2x, which is little f of x, and that was exactly my criterion for being called an antiderivative. I also realize that my most general antiderivative has a plus c term. That plus c term just gets differentiated to 0 in big F prime, so it doesn't have any change to this over here, still an antiderivative. And it is the most general antiderivative, which follows from the proof we did in section 4.2. So what about little f equals sine x? What is its antiderivative? Or what function has a derivative that's sine x? Well, here it might be a little tricky, but I know that it probably is something like cos x. Except that the derivative of cos x is negative sine x, which isn't quite little f. So I got negative sine x. I want positive sine x. Can I fix this? Well, if I come back here and put a negative in front of the cosine x, the derivative of negative cos x is going to be negative sine x, or positive sine x, which is f of x. I always throw in my plus c to make it the most general antiderivative, and there we go. So a table lookup didn't quite get me the exact answer right away in this case, but it got me pretty close, and I could massage it a little bit to make the details work out. All right, f of x equals x to the n, where n is not -1. So I want to differentiate something and end up with x to the n. I know when I differentiate a power function, I take 1 off the power. So I'm going to start with something like x to the n plus 1. That seems like a pretty good starting place. That would tell me that f prime of x is Well, I bring the power down and I take 1 off the power. Well, this x to the n is what I want. I don't want that n plus 1. How do I get rid of the factor of n plus 1? Well, that's just a constant factor. If I divide by it over here, that constant just comes out of the derivative, divides out. This is equal to little f of x. So x to the n plus 1 over n plus 1 is an antiderivative of little f. And the most general antiderivative then would be this antiderivative with plus c. Note that I said n not equal to -1 here. What's the antiderivative of 1 over x? We do have to be a little bit careful here. I mean, if I just jumped right into it, I might think x to the n plus 1 over n plus 1, but that gives me like x to the 0 over 0, and that doesn't really work out. But I might immediately realize, oh, wait, I know a function whose derivative is 1 over x, that's log x. The derivative of log x is 1 over x, which is little f of x. Here I can write plus c, and there is a little bit of a nuance here. If I really want the most general antiderivative, I probably ought to have log absolute value of x. Remember, the derivative of log x for x positive is 1 over x, but the derivative of log absolute x for x not equal to 0 is 1 over x. So we could actually expand our horizons to a larger swath of the real line, all real numbers except 0, if we go this route. So I really ought to have log absolute x if I'm looking for the most general antiderivative. And this discussion was part of logarithmic differentiation back in chapter 3. So if you need a refresher on that, take a look back there when we talked about logarithms and differentiating logs and all of that. Logarithmic differentiation, implicit differentiation used all of those kinds of ideas. And then I have some more challenging antiderivatives. Something like x times e to the x squared. Well, here I've got to take maybe a little bit of an educated guess. If I want something to differentiate to look like something that has an e to the x squared in it, it's probably got to start with an e to the x squared, because e to the stuff differentiates the e to the stuff. I don't think anything else is going to differentiate and look like e to the x squared. Okay, let's take that as a starting point. I'm going to take the simplest thing that I can kind of as a starting point. See what happens, make an adjustment, see how that impacts the adjustment, and so on. Or see how that impacts the derivative, I meant, see how the adjustment impacts the derivative, and so on. My derivative is e to the x squared. E to the stuff differentiates to e to the stuff times the derivative of x squared, which is 2x. Well, hey, that's pretty close to actually what I want. X e to the x squared is what I want. Can I just divide by 2 and make that go away? Yeah, I can. And then to make it the most general antiderivative, I found an antiderivative, 1/2 e to the x squared. To make it the most general, I just add c. Okay, then what about this one? Little f of x equals e to the x squared. Again, I might think big F equals e to the x squared is a good place to start. I end up with 2x e to the x squared. This is the bit I want to keep. I want to get rid of that bit. So maybe I come over here and I do 1 over 2x e to the x squared. Did I solve my problem? Do I just put a 2x here and equals little f? Well, no, we have to be careful. Let's not be too flippant about things. If I try something like this, well, now I have something like a product rule or a quotient rule that comes into play. It doesn't, the derivative doesn't look like anything like this anymore. So that wouldn't be the solution. In fact, uh, this function, e to the x squared, it's a pretty nice function. It's not, some crazy off the wall function. It doesn't have an antiderivative that can be written in terms of nice, standard combinations and compositions of functions. So we would have to do something like write this as like an infinitely long polynomial or something like that. Something that we would look at in calculus too. But for our purposes, there's really no antiderivative that can be written in what we call closed form. That can be written as combinations and compositions of nice functions, our standard catalog of functions, power functions and trig functions, exponential, things like that. So, there's in some sense no antiderivative. Speaking in terms of closed form that we're looking for, in terms of combinations and compositions of our standard functions. In theory, there's an antiderivative. That's, but we can't write it down. We can't work with it or, write it down algebraically or manipulate it in nice ways or evaluate it, anything like that. So that's why I'm writing this kind of in quotes. And we do have to be quite careful that when we make a change, like I did up here, when I translate that change over to the derivative, I have to be making sure in the back of my mind, okay, when I do the derivative, all that I did is multiply by a constant. That constant will just pop out in front of the derivative and we'll just stay out in front of the derivative over here as well. So I don't want to be too flippant about, fixing my guess for antiderivatives. I need to make sure that each time that I make an adjustment uh, and then let that adjustment propagate through to the derivative, that I am actually using good technique and valid uh, properties and theorems and so on. Okay, so we have a nice theorem. If big F is an antiderivative of little f and big G of little g, then we can say two things. Big F plus big G is an antiderivative of little f plus little g, and C times big F is an antiderivative of C times little f. In other words, anti-differentiation is linear. If I want to take the antiderivative of a sum, I can take the antiderivative of each term individually and then add them together. Or if I want to take the antiderivative of a constant times a function, I can take the antiderivative of the function and then just slap the constant in front. Be really careful. This can lead a lot of folks astray. The same is not true for products. Just like how the derivative of a product is not the product of the derivatives, we can't differentiate each component factor individually and multiply them together to get the derivative. We have the product rule that we'd have to use. Well, anti-differentiation also has that same restriction that the product of the antiderivatives is typically not the antiderivative of the product. So be careful with that. Okay, let's look at this example. Let's try to find u of x such that u prime equals x squared plus 9x. And here we have an extra little interesting piece, and u of 0 equals 4. So I want u prime be x squared plus sine x. I need to anti-differentiate this to figure out what u is. Well, to differentiate x squared, I saw up here, I basically proved a theorem here, essentially, that the antiderivative of x to the n is x to the n plus 1 over n plus 1 plus c. Or this is 1/3 x cubed. If I check this when I differentiate this, x cubed differentiates to 3x squared, I get the x squared, and the 3/3 goes away. If I anti-differentiate sine x, I get minus cos x. If I differentiate cos x, I get negative sine x. The negatives cancel, and I get plus sine x, which looks good. And then I get plus c. So this is my u of x. Now, when I have a plus c like this, when I have a parameter like this, essentially what I have is like a family of curves. Maybe this is the curve where c equals 0, and this is when c equals 1, c equals 2, c equals -1, and so on, right? And there are, of course, curves in between these that all at all of the fractional points or all of the irrational values for c. C could be any real number. I'm just drawing a few to illustrate the point. Now, if I want u of 0 to be 4, that means I want to go through the point, say 0, 4, maybe that's like here. Well, that plucks out one member of this family of curves. I don't know if the answer is actually c equals 2. I'm just illustrating it. That plucks out one member of this family of curves that determines what c has to be. So I have 1 degree of freedom, c, that can be chosen as any real number. If I impose one constraint, that I want my solution curve to pass through a particular point in the xy plane, then that plucks out one member of that family and tells me what c has to be. So when x equals 0, I want u to be 4. Or in other words, 4 equals 1/3 times 0 cubed minus cos 0 plus c, or 4 equals 0 minus 1 plus c, says that c equals 5. So then my u of x that both has the property that its derivative is x squared plus sine x, and also has the property that u of 0 equals 4, is 1/3 x cubed minus cos x plus 5. Any questions on that one? Okay, let's try to find big F such that big F prime equals x or absolute x plus 2. Oh, so this is big F prime. I see that this is a piecewise function. This is going to be x plus 2 for x is bigger than -2, when x plus 2 is bigger than 0. And it's going to be the negative of x plus 2, or negative x minus 2, for x less than -2. And let's say there's going to be x plus 2 for x bigger than or equal to -2. So I can compute an antiderivative on each of these intervals. So I can say on the interval, what, -2 to infinity, I can compute an antiderivative. So what would big F be on this interval? Well, I know that big F prime on this interval is just x plus 2, whose derivative looks like x. That's going to be x squared, and we need a 1/2 in front, and then plus 2x. 2x differentiates the 2. I do need an arbitrary constant, so I'll do plus c. So this is my antiderivative on the interval -2 to infinity. What else do I know? Well, on -infinity to -2, I know that big F prime is -x minus 2. So big F is just going to be -1/2 x squared minus 2x. I don't want to use plus c here because I already used that. These could be two different arbitrary constants. I'll call this maybe plus a d. Now I do want my antiderivative for this function to be continuous at -2. So if I do, say, f at -2 from above, looking at the on -2 to infinity side of things, I get 1/2 times -2 squared is 4, plus 2 times -2 plus c, or that tells me that what, 4 over 2 is 2, minus 4 is -2 plus c. On the other hand, f at -2 from below, evaluating big F of x at -2 when we're on this interval, gives me -1/2 times -2 squared is 4, minus 2 times -2 plus d, or that's -2 plus 4 plus d, or that's 2 plus d. So I want to require that 2 plus d equals -2 plus c. Or maybe I'll make d equal what? C minus 4. So then what is big F? Well, on -2 to infinity, for x bigger than -2, bigger than or equal to -2, we have this. And for x less than -2, we've got this one with c minus 4. And then plus d, or that's minus 4 plus c. And we actually see these are quadratics. So little note here, anti-differentiation is a smoothing operation. It takes corners or sharp edges like this and smooths them out. It takes jumps and turns them into corners, kind of loosely speaking. Differentiation goes the opposite direction. It's kind of anti-smoothing. It can introduce corners or jumps into into a derivative. So when we anti-differentiate, or later on when we talk about integration or integrating a function, that's a smoothing operation. So there are things um, like long run averages, things like that, that are closely related to anti-differentiation and integration and so on, kind of smoothing out the noise in the system. Um, So there are also like PID controllers. That's another example where the integration part is, and these are for something like, an autopilot or like a cruise control or something like that. The integration part kind of takes in a bunch of information from the past, kind of uh, and kind of incorporates it all together into something that I suppose tries to use information from the past to predict the future, is maybe like a way to put it. Um, so this idea can be pretty widely applied, and I think is a pretty important idea in a lot of different engineering fields. So the understanding that anti-differentiation or integration in chapter 5 is a smoothing operation. It can kind of like denoise things in some sense. Okay, another example. Suppose that a particle starts moving at position s equals 0 at time t equals 0, and its velocity is given by v of t equals 3 sine of 2t. What's the location of the particle at t equals pi? Well, I want to find s of t, the position function for the particle, and I know that s prime of t equals v of t. So I know s prime of t is 3 sine of 2t. I want to find s, so I want to anti-differentiate. Well, what differentiates the sine? That's going to be something like cosine. So I'm going to start with cosine of 2t. If I differentiate that, I get negative sine of 2t, and then times a factor of 2 that comes out. I don't want a factor of 2, I want a factor of 3 instead, so I've got to multiply by 3 halves. So when I differentiate cosine of stuff, I get negative sine of stuff. The negative times the negative cancels and give me sine of stuff, exactly what I want. The chain rule pops out a factor of 2, which cancels the 2 on the bottom and leaves me with 3, which is also exactly what I want. And then I have plus c for my arbitrary constant. So this is my family of functions s of t. This is my family of position functions that would have this velocity function associated with them. And this makes sense that we'd have a family of functions, because if you think, velocity, even if we took a simple velocity function, if you're standing here and you say, I pointed myself in the direction northwest and went, walked straight 3 miles an hour, well, you could have started from Pittsburgh, Pennsylvania, or Wheeling, West Virginia, or Los Angeles, California, and you would have had the same velocity function. I suppose if we assume the Earth is flat, you'd have the same velocity function, but you'd have started in very different places. So you'd have a very different actual path. Your position is going to depend on where you start, even though all of these people will be kind of moving along parallel paths in these different, that started in these different cities. They'll kind of maintain all of their relative positions to one another as they evolve forward, but they'll be following different paths. So we know that s of 0 equals 0. So we'll apply our initial constraint. So that's negative 3 halves times cos of 0 is 1 plus c. That's going to equal 0. So c equals 3 halves. So then my specific member of this family of functions, that's the position function for this particle at that starting point, s of t equals, I guess I would get 3 halves times 1 minus cos of 2t. Probably the nicest way to write it. All right, any questions on anti-differentiation, anything on chapter 4, or really differentiation as a whole? Because when we move into chapter 5, we're really gonna switch gears into integration, which is a very different idea. At least at first glance, seemingly completely unrelated to anything we've done so far. So any questions before we jump into chapter 5? Okay, so down to chapter 5 then. So shifting gears like really completely, pulling a 180 here. We're starting into a completely different topic. Now, I think, back in the olden days, before even I went to college, I think usually Calc 1 was like differentiation, and Calc 2 was integration, and Calc 3 was like multivariable everything. But, the demands have gotten a little more, the expectations have gotten a little higher. So we've put like vector calc into Calc 3 and some other stuff, and mechanics and stuff into Calc 3. And that pushed a little bit of the three-dimensional stuff, like with 3D geometry and different types of like dot and cross products, things like that, into Calc 2. And I think that kind of pushed a little bit of what used to be Calc 2 into Calc 1. So it seems a little strange that we're kind of, why are we shifting gears so drastically kind of right at the end of the semester? Well, because this stuff really meshes with the Calc 2 material, but we're just covering more in 3 semesters of Calc these days, so the dividing lines have gotten a little bit blurred. That's also why Calc is a 4-credit course. It's a 4-credit course at CCAC, but also at a lot of other places, even places that typically have 3-credit math courses. Calc will often be 4 credits, to the bane of all registrars who have to figure out how to schedule 4-credit courses in line with 3-credit courses. But in some places, I think do run it, a little bit differently, where they have like a partial semester for each of the different topics or something. I don't know, or you can be MIT and just cover 3 semesters of material in 2 semesters, and you know, uh, but but that's kind of the rarity. Okay, so jumping into chapter 5, integrals, we're going to kind of start a little bit like the way we did with derivatives. We started with a particular problem, kind of a motivating idea. Why do we want to develop this idea any further? What kind of problems can we solve? And the problem we're going to focus on is the area problem. So let's start with an easy area problem. Oh, need a little more room than that. Let's start with an easy area problem. Let's try to find the area under the curve. We'll say exactly what we mean by that in a second. The area under the curve y equals 3x plus 2 between x equals 0 and x equals 4. So here I have an x-axis from going from 0 to 4, and y equals 3x plus 2. Well, when y is 0, or sorry, when x is 0, y is 2. When x is 4, y is 14. So I have this line going between 0, 2 and 4, 14. That's my curve of interest. Now, area under the curve means the signed area between the curve and the x-axis. So I have the x-axis here, and I imagine kind of dropping a perpendicular down. And this creates a shape, a trapezoid. And I have some area of that curve. In this case, that area will be positive. If in another example, if we had a shape that was below the x-axis like this, this area would be negative because it's associated with negative y outputs. If the area that I'm looking at is associated with positive y outputs, right, the y coordinates in blue here, the y's are positive, but in the red over here, the y's are negative. So that's what we mean by signed area. It respects the sign of the y coordinates in the area, in the region. If we had a figure that kind of crossed over, was sometimes positive, sometimes negative, then we would take the region above the x-axis, we would consider that positive area, and the region below consider that negative, and probably treat the two independently, or at least that's how we would visualize it at this point. It turns out that we don't have to think so much about sine uh, after a little while, after we get a couple sections in, but for now we do have to think about that. Okay, so what is this area? Well, nicely enough, this area has all flat sides. I can just use basic geometry. I know that the area is, well, it's the base width, 4 minus 0, times the average of the heights, 2 plus 14 over 2. 16 over 2 is 8. 4 eighths are 32. It is positive because it's above the x-axis. It's associated with a positive y value. So my area, my signed area under the curve is positive 32. I have a little bit of an issue with this next example, though. Find the area under the curve, y equals 4x cubed, between x equals 0 and x equals 4. I'm going to try to draw this pretty nicely here. So 4x cubed when x is 0 is 0. And then 4, and eventually I get to 4 to the 4th power, or that's 2 to the 8th. What is that, 256? So this has got to be 256 up here. So 1 comma 4 is like almost at a height of 0. 2 comma 2 cubed times 4, that's 8 times 4, that's 32. That's like maybe 10% of the way up. 3 cubed is 27 times 4, that's like 120-ish. What is that, 128? So like that. So I think my curve looks something like this. And because I want to draw this a couple of times, I'm going to screen cap it. Oh. I'm trying to move it to a better spot. There we go. Come on, there we go. All right. So because I want to use it over and over, I'm going to screen cap it like that so that it stays pretty consistent. So the area that I want is this area here. This is going to be positive, so we don't really have to think too much about the sign here. We're just going to try to figure out how to get the value of this area. Now, the problem is that, I mean, I have a couple of flat sides, but the problem is that this curve is not flat. And essentially all of my geometry deals with flat sides. I mean, maybe I have like, circles and things like that, or ellipses, but this also doesn't fall into those categories. And we even saw that with like circles and ellipses, well, just to find the area of a circle, we already had to use calculus. So how could I find the area under this curve? Well, the basic idea here and the area problem is that I can approximate the area under the curve with boxes. So maybe what I could do is, say, make a box that goes like this, one that goes like that, one that goes like this, and like that. And these boxes, the area of each of these boxes, when added together, will give me an upper bound for the area of the curve I'm looking for. from the area for the area under the curve, the area that I'm looking for. And then maybe I could do something like this. I can make boxes that have height kind of at the left end point of each of these intervals. I could figure out the areas of each of these boxes. Areas of boxes are easy to figure out, right? Just base width times height. And that would give me a lower bound for the area I'm looking for. So I have some area up here. My area is A. And my problem is to find A. And here I have an upper bound for that area. And down here I have a lower bound for the area. So I see that A is bigger than L and less than U. So that gets me bounds on the area. But if we think back to how we evaluated the area of a circle, we kind of took these bounds and then refined and refined and refined them to get closer and closer so that hopefully U and L will kind of tighten into the same number, and by the squeeze theorem, tell me exactly what the area is. Can I do that here? Well, maybe what I'll do, instead of calling this U, maybe I'll call it U4. I chose to use 4 boxes here, but I could have used instead, I mean, could I have used 8 boxes? Could I have done it like this? Right. This would still be an overestimate, but it would have gotten rid of some of the excess, right? There's like a little rectangle here that I had in the green estimate, but not in the red estimate. I've gotten rid of some of the excess. It's still an overestimate, but it's a smaller overestimate. So U4 is bigger than U8, but U8 is still bigger than the area. Or I could do something similar down here. I could use, instead of 4 boxes, maybe I call this L4. I could instead use 8 boxes. I'm setting my height to kind of align with the left endpoint. And so on. And I see that I still have a lower bound. My red area from all of these is still less than the area A, but I've kind of filled in some of the empty area. So L8 is bigger than L4, but is still a lower bound for the area. So basically what I have here is that U4 is bigger than U8, which is bigger than the area, bigger than L8, bigger than L4. By going from 4 boxes to 8 boxes, I have maintained an upper and lower bound, but I've tightened those in closer to the area. So wouldn't it be super nice if I could come up with a UN and an LN such that UN goes to some number. Let's give it an actual number. Let's say R. I don't know why I picked R, but let's just say it's R as n goes to infinity. And ln also goes to R. Then this would imply by the squeeze theorem that A equals R. So this is kind of our goal here. Now, one little caveat. Some of you might have been exposed to calculus a little bit before, and you might say, there's this idea of Riemann sums and so on. That's clearly what we're trying to kind of head toward here. But this isn't quite how Riemann sums work. And that's true. This is a little bit different than how Riemann sums work. So if you're saying, wait, I thought I remembered it this way, but this is a little different. Am I remembering wrong? No, you're probably not remembering wrong, but we're doing things a little bit differently than Riemann sums here for the purposes of illustration. And then we'll kind of discuss that in the next section on the definite integral. So just in case this reminds you of something but isn't quite the same, you know, you're not going crazy. It's, you know, it's slightly different than Riemann sums, what we're doing here. But this is what we're hoping for. So we'd like to find UN and LN. I'm going to leave it as an exercise. I should just say exercise, do the rest of it and call it a day, but exercise, find LN. There's always a joke that when the problem is too difficult for the professor to figure out, then they just leave it as an exercise. But in this case, I think LN is actually the easier of the two sums to compute, though. So we're going to find UN. We're going to find this one here. So I need to grab another copy of this. So we will work on finding UN. And as an aside, this does work for this problem. If we came up with a UN and an LN that were upper and lower bounds, but they converged to two numbers that were, you know, different, if one converged to, you know, 100 and the other one 200, all that would really show is that my area is between 100 and 200. So that wouldn't be super helpful. But in the case of this problem, this actually does work. So when we find UN, find its limit, we will actually find the area, but to actually prove that that's the area, you would do the same thing with LN. You would find LN, take its limit, and show that the two limits equal the same number. So this exercise kind of gives the other side, the other half of that proof to be able to apply the squeeze theorem appropriately. But we're going to find UN and then see what it goes to as n goes to infinity. All right. So let's start with what is U1. Well, U1 would be using one box over this entire width. So that box would have base width 4 minus 0, and it would have height. We're aligning to the right side because in any interval under consideration, because 4x cubed is an increasing function on this interval 0 to 4, the maximum height is going to be on the right endpoint. So we're always aligning the height of our box with the right side for UN. For LN, we're always aligning with the left side. That's going to give the minimum height. So f of 4. Remember, f of x is 4x cubed. Or what's U2? Well, now I notice that each of my boxes has base width 2. So I get 2 minus 0, f of 2, plus 4 minus 2, f of 4. So this first one was really just 4, f of 4. This next one, each box has the same base width. Each box has the width 2. So I can kind of factor that out. And then I get f of 2 plus f of 4. Or U4. Well, now if I use 4 boxes, each one is going to have base width 1. So it's going to be 1 f of 1 plus 1 f of 2 plus 1 f of 3 plus 1 f of 4. Or that's just 1 times f of 1 plus f of 2 plus f of 3 plus f of 4. Okay, so if I use n boxes, I see I'm going to end up with base width times some stuff with the function heights. My base width is going to be 4 minus 0 over n. When I used one box, I had 4 minus 0 over 1. When I used two boxes, 4 minus 0 over 2, four boxes, 4 minus 0 over 3, etc. Or writing it a little nicer, it's just going to be 4 over n for my base width. So as n increases, the width of each box decreases, and kind of each box's area gets smaller, but there are more boxes we're adding together. We're going to use summation notation. So a little aside on summation notation. If I have a bunch of things I'm adding together, say x1 plus x2 plus x3 and so on out through xn, I can write them in this capital sigma notation. You might or might not have seen this before. I think most people have seen it, at least here or there, but you know, maybe you don't know exactly what it means. What it stands for is I see that there's a pattern in the things I'm adding together. I write kind of the general form of that pattern in here, x sub k, and I sum, this is capital sigma, so standing for the letter S, I sum from k equals 1 up to n. The understood thing is that we are indexing over the positive integers. So k goes from 1 to 2 to 3 to 4 until it gets to n, which we would think of as n as a positive integer as well. So sum k equals 1 to n of x sub k means do x1 plus x2 plus x3, etc. If I wanted the sum of a bunch of things squared, I would write xk squared and sum that from k equals 1 to n. Or if I had, say, f of x1 plus f of x2, etc., I would take the sum from k equals 1 to n of f of xk. So a few examples. Sum k equals 1 to n of 1. Well, this is just when k equals 1, we have a 1. When k equals 2, we have a 1, etc. Out to when k equals n, we have a 1. We just have n copies of 1 added together. Well, that's just n. Or this is kind of a famous formula. Sum k equals 1 to n of k. When k is 1, we have 1. When k is 2, we have 2. When k is 3, we have 3, and so on. The sum of the first n positive integers. And it turns out there's a few different proofs of this, but turns out this is n times n plus 1 divided by 2. Okay, so, and there are some others down here, but we'll talk about those a bit later. So I know that I have n boxes at this point for un. So I'm thinking of something like this. So my intervals go, so my intervals under consideration go from, say, 0 to 4 over n, then from 4 over n to, oh, 2 times 4 over n. There we go. Then from 2 times 4, my fours keep turning into nines. Let me zoom in a little bit. From 2 times 4 over n to 3 times 4 over n, and so on. Out to here, we have n minus 1 times 4 over n to n times 4 over n, but that's just 4. So these are my intervals. So when n is 8, I go from 0 to 4/8 or 0 to 1/2. And then I go from 4/8 to 2 times 4/8, from 1/2 to 8/8 or 1, from 2 times 4/8 to 3 times 4/8, and so on. Those are my intervals. I want to take the right endpoint at each of these. So I want to take f at what's my input. Whoops, skip the step here. I want to sum up. We'll say from k equals 1 to n over my n boxes. I want to sum up f of what's my input into my function. It's always at the right endpoint. So it's going to be k times 4 over n. Or I have, let me write it all in one color here. Or I have un, the upper bound to the area for n boxes is going to be 4 over n times the sum k equals 1 to n, f of k times 4 over n. So that's what un is going to be. Now it's important that this is only an upper bound. I've only chosen the right endpoint of every one of these. This is only an upper bound because this is increasing. If this function was going up and down, or if it was decreasing, then I wouldn't have an upper bound here. So I'm leveraging the fact that this is an increasing function, so its max output is always associated with the max input, or the rightmost endpoint of each interval. So what's f of k times 4 over n? F of x is 4x cubed. Don't know where that came from. Um, f of x is 4x cubed. So there we go. So 4 times this input, 4k over n cubed. All right, so I have un written in this form, but unfortunately writing a function in summation form like this isn't super helpful, right? If n is really big, it's just a lot of work to compute it. And to take a limit as n goes to infinity, I have more and more and more terms. It's not obvious how to make that work. One thing that I notice is that this is just a finite sum. I can imagine it breaking into a whole bunch of different terms added together, and then I can apply algebra to those terms. So I can, for instance, say that the summation of the sum of two terms, I can break the two summations apart. Or if I have the sum of like a times f of xk, sum of a constant times some stuff that depends on k, my index for the sum, the constant can just factor out in front. Right? The same way that if I had, say in this example here, 3 times 1 plus 3 times 4 plus 3 times 9, and so on, plus 3 times n squared. This could be 3 times 1 plus 4 out to n squared, right? So I can factor constants out of sums as long as the thing I'm factoring out doesn't depend on the index of the sum, k. Okay, so writing this a little differently, I have oh, not equals, sum k equals 1 to n. I have a factor of 4 here. I have 4k over n cubed, so that's 4 cubed, k cubed over n cubed. My index of my summation is k. So k is the only thing that's changing from one term to the next. So this k cubed cannot come out in front of the sum. It has to stay inside of the sum. However, 4 times 4 cubed, that that doesn't change. That doesn't depend on k. Even the n cubed, that actually also doesn't depend on k. That stuff can all come out front. So I have 4 over n. The 4 cubed times 4, or 4 to the fourth. Why did I pick a problem with so many 4s in it? 4 cubed times 4, 4 to the fourth comes out front. The over n cubed comes out front. And then I have sum k equals 1 to n of k cubed. Now, the same way that we have like the sum k equals 1 to n of what basically is k to the 0 is n. Sum k equals 1 to k, or sum k equals 1 to n of k to the first has this nice closed formula in terms of n. We can do the same thing for k squared or even k cubed. It turns out that the sum of the first n cubes is this thing here. It happens to be the exact square of this. N times n plus 1 over 2 all squared. So I have un equals 4 to the fifth over n to the fourth times n plus 1 over 2 all squared. And I'm almost there. The 2 squared, the 2 in the denominator that gets squared, divides out one of the factors of 4 to the fifth, leaving me with 4 to the fourth. And let me write that down here. And then I end up with n squared times n plus 1 squared over n to the fourth. N to the fourth. So for n boxes, this is my upper bound. And this will always be bigger than the area. What is un? What does un go to as n goes to infinity? Well, this is just a rational function in n. It's a quartic over a quartic. As n goes to infinity, we just look at the leading coefficients, but the leading coefficients in both the numerator and denominator are 1. This whole bit just goes to 1 in the brackets, 4 to the fourth. So I see that un goes to 4 to the fourth, or 2 to the eighth. What is that? 256. Un goes to 256. Now, it does turn out that ln also goes to 256. These two things, along with the fact that un is an upper bound for a and ln is a lower bound for a, these all come together to say that a equals 256. That was quite a bit of work to solve an area problem. The good news is that in a section or two, we'll see that practically computing such areas in a lot of circumstances is much easier than the way we did it here. But we're starting from first principles, building up the idea. When we look at definite integrals next time, we'll kind of take a slightly different perspective on this general kind of idea using boxes to make estimates of areas. And then in section 3, we'll see the fundamental theorem of calculus, which will be an enormously helpful tool in our toolbox to compute such areas and to do a lot of other things as well. Are there any questions on anything from today? Any of this material? Okay, then we will end class for today.